Okay, so my name is Yevgeny Bar Lev. I'm from Ben Gurion University. So after you were properly brought to proper condition after the last lecture, I'm going to continue with a much simpler minded approach of a physicist. Although I'm going to show you, given the nature of the audience, I'm going to show you some lemmas and theorems, but I'm not going to even make an attempt to prove them, but just state them as results so you can connect. But it is going to be a board talk, mostly due to my laziness, but not that I want to be rigorous. So I'm going to talk to you about emergent randomness and deterministic quantum systems. Basically, the premises is going to be that we have a system. The system is described by something which is called Hamiltonian, which I'm going to call H, but you can think about it as a matrix. And this matrix has the property that the expectation of this matrix is just gives us the energy of the system. The matrix is Hermitian. And it has eigenvalues. What? Expectation with respect to some pure state. Yes. If in any state the notations are not clear, like I'm not sure if the bracket notations are obvious. Yes, okay. So please tell me, because I really don't have experience talking to a mixed audience. So this is the setting, and we are going to look on some observable. Which I'm going to call it A. And what is going to be important, not now, but a bit later, is that A is local. So when I plot it in this way, this literally means space, right? Not just a box, okay? So local, it means that the observable lives in some place in this space, okay? So this is the premises. And now what we're going to ask is, or I'm going to define basically, is a thermalization. And the definition is going to be an approach of local observables to equilibrium, to thermal equilibrium. Okay, and the way it looks is very simple. So if I plot the expectation value of this observable with respect again some state as a function of time. Okay, so we are going to start with, maybe I'll use colors for better dramatic effect. So it's going to start with some value, and then is going to approach a constant value. And this constant value, I'm going to call it a thermal, or which is the thermal equilibrium. I'm going to define it in a second. So the thermal equilibrium, there's not a lot of space, but we'll do our best. So the thermal equilibrium is defined as the trace over a Gibbs state. Let me write it like this. So Dorit told me that you know what is a Gibbs state. If not, do ask with some normalization. Z is normalization. And the questions that we are going to ask, okay, another thing that I want to add is that the state, the evolution of the state here, psi of t, I will put it here, it is given by the Schrödinger equation. The solution is, this is the solution, this is psi, the initial state. Okay?
But you cannot this directly.
What?
Well, currents will, I mean, you will not have really thermalization, you will have sometimes jumps, you mean?
It's infinite. I'm going to define everything, don't worry. Okay? That's the definition of thermalization. Okay?
But with this definition, it doesn't exist because you will have.
It exists in a certain limit. I did not say still what I want. In an infinite system, this is exactly what's going to happen. Okay? And also for, I'm also going to say for a finite system how well it's going to happen. So you're going to be satisfied. Okay? I hope. Huh?
H is a matrix. You know, is it random matrix? What is H?
Whatever metrics. I'm not going to, since I was asked not to talk about models, it's going to be just a matrix. Okay? Also for you, Ivan. No, okay. I still didn't say what are the requirements of H. That's going to be the. I'm coming to the question.
So you said tell us.
So the main question is like this. Okay, so we have an observable A of t. Okay, which is evolving in this way. Okay, and I can write it down. Okay, I can insert here. So I can write it down. Let me do it in a bit silly way. Again, I'm sorry that I'm really doing trivial stuff compared to the previous lecture, but I can insert here the energy basis. Okay, and here I can insert another one. Okay, and if I do this, I'm going to.
What is that?
He's sitting there, I don't know. And now I'm going to I'm not. הצלם יושב שם, אבל הוא לא...
זה לא קשור אליי, זה קונטרול... זה קשור למצלמות, למערכת הפנימית.
לא, אבל
ואז יראו, השאלה היא מה רואים. אני יכול לעשות. פה רואים? לא. אני לא יודע מי דיבר. מה? יש? Okay, so this is the evolution of the observable, very simple. We are going to define this, we are going to call this coefficient as C alpha. Okay, and then we have that it's C alpha squared A alpha alpha. This is the diagonal contribution. I'm sorry that I'm doing it slowly, but it's going to be a sort of important later. This is going to be the main thing. C alpha, C beta, E alpha minus alpha beta t. Okay, so this is the evolution of the observable. And what you see here is two things. The first thing is an expression which does not depend on time. Yes, I am. Thank you, Yossi. You're sharp eye. Doesn't depend on time. Okay, so this is going to be connected to this red plateau. Okay, the value of this red plateau. So we are going to call this a diag for diagonal elements. Okay, and the main question is, okay, that's going to be the first question, is it equal to the thermal one? It's not obvious that it's supposed to be, and it's not for any Hamiltonian that we want. That's one question. This is the diagonal, this is this guy, and is it equal to the thermal? And then the other thing that we want is that this goes to 0. How? And this connected to your question, with system size. If the system size grows to infinity, this guy vanishes. Okay? So this is what we would like to have.
Like you said, no model.
It's of course going to depend on the models, right? But it's going to be very generic result. But still, the Hamiltonian, the models. There's going to be a very important assumptions at the end on the Hamiltonians, okay? But not right now. I'm just stating the question and the problem, okay? So we have first question is does it thermalize to does it go to equilibrium, and are those fluctuations vanishing? Okay, the answer from experiments in the lab, we know that it does happen. Coffee thermalizes, so stuff reached to equilibrium, but we have a question because, as you see here, the result appears to depend on the initial conditions. Okay, the initial conditions are C alpha, so this is here, it's defined here, I remind you. It depends on the initial conditions, but we know in the physics or also from basic experience that nothing depends on the initial conditions except that they just set the energy, the initial energy, okay? But otherwise, all initial conditions with the same energy are going to reach to the same equilibrium, which is defined by this matrix. So how is it possible?
Just to be clear,
Yeah.
this is very different than coffee in the lab because we're
Yes,
not at the
agreed,
system.
agreed. So it's coffee in an isolated lab. Okay? Good.
I said in the cup.
Isolated cup, a thermos, yeah.
What is the temperature of the thermal system you approach to?
The initial energy. Okay, we'll talk about it. Okay, but the problem is it clear? So we have a unitary evolution which gives us this expression, but it depends on the initial condition. But somehow we are approaching a state which does not depend on the initial condition. Okay. Another way to look on it, which maybe is going to be more helpful for some of you, is that if you look on the state here, we are always in the unitary evolution. We are always in a pure state. Okay, we started with a pure state and we continue with a pure state, but the resulting state is a mixed state. Okay, so how is this possible? Okay, so how is it possible that from one copy of a system we get basically a random collection, an ensemble of systems? So this is the question, and this is basically a very, very long way to explain where is the randomness and where is the deterministic system. So this is the deterministic system, so this is the randomness. Now we're going to try to connect. Okay, so if you understand the premises, now we are going to start first. So I'm doing it in a very non-traditional way. I mean, like in the way it is done in the physical community, because I'm trying to connect to the mathematicians in the audience and also the computer scientists. So I'm going to start in a way that makes some physics people maybe uncomfortable. but I think it's easy and pedagogical. So what we are going to assume first is that we already have randomness, and we are going to assume that we are leaving that all of our states are random, and in which sense I'm going to explain in a second, in exactly the same sense that basically was described during this workshop. I don't know how to call it, meeting. So basically we are going to assume now first randomness, and then what I'm going to do, I'm going to relax this assumption a little bit, and we are going to, at the end, get to the eigenstate thermalization hypothesis, which is essentially connected to the pseudo-random notion, which was discussed here. That's the goal, but let's see how it works. Okay, so let's now it's going to be kind of statement of rigorous things. So we assume a random or R random. You know what R random state is? State. Okay. So we have psi, and I'm sure that it was drawn here in some way, that we can think that our Hilbert space is some kind of a sphere. If the dimension of the Hilbert space H is D, then we have then this sphere is 2 to the D minus 1 dimensions, and each one of those psi's can be thought as a vector on this sphere, and the distribution is uniform, the Hard distribution is uniform, so each psi is uniformly covering this sphere. Okay, so this is the randomness. And now what we are going to do is we are going to say some results about, so this is basically a property of high dimensional spheres, which are, for me, are extremely not intuitive, but maybe for you guys they are. And I'm going to start with what is called Levy's lemma. So I'm going to tell you when stuff are going to stop being rigorous. This is rigorous. So Levy's lemma says that assume we have a function of psi. Okay, so it's a scalar function on this sphere. Okay, and it is sufficiently smooth. I'm not a mathematician, so I'm not stating exactly what does it mean. Sufficiently smooth.
Now you're stating concentration of measure?
Yes. And so this is Levy's lemma, which is, yes, it uses concentration of measure. What Levy's lemma says is basically that for any function on a high dimensional sphere, the value of the function is exponentially close to its average. Okay, it's, I don't know, for me it's extremely not intuitive, but I don't. So it basically says that the distance between psi and its average, let's do it like this. Okay, so the probability to find is exponentially small, and it's exponentially small. Okay, so there is some constant here, and it's exponentially small with the Hilbert space, well, the dimension of the sphere. Okay, it's a geometrical statement. So this is super awkward. There is an epsilon, of course, dependence. Guess it's here somewhere. Here there is another constant I wrote. So this constant depends on the smoothness of the function. So there's various stuff. Now,
Epsilon can't be downstairs, can it?
is it supposed to be? Yes, upstairs. Yes, you're right. I promised you there's going to be a lot of non-rigorous business going on. But what is important is not what I wrote here is that the statement is that the function is very close to its average, exponentially close. Over this psi. Okay, so psi is randomly distributed. No, not yet. Not yet. They are going to be. They are going to be. Currently, I'm assuming that there is a random psi, okay? And we are going to get, covering the sphere, and we are going to get to the eigenfunctions soon. Okay? So this is the statement. Now, what can we get from it? So, for example, if we look on the F, we have another one. Average over the sphere.
This is not true. So the function is not its average. The set where it's not its average is a very small set.
It's really weird. So the function is varying over the sphere.
Yes.
But if you like integrate over the sphere over the function, you get this number, and it's very, very close to the value of the function in any point on the sphere. Extremely awkward, but this is a rigorous statement. Okay.
The equation is basically that the equator is in high-dimensional spheres is all of the sphere. So you can try to come up with a counter-example, put half the sphere 0, half the sphere 1,
Yes.
and do continuous something on the equator. That thing.
Okay. So what we are going to do with it? Okay, this is now a geometric statement. So I'm going to take f psi to be the expectation value. Currently, this observable actually doesn't need to be local, so I'm going to tell when it will. Okay, and you immediately see an important result just coming from this mathematical geometrical lemma. This tells you that the average of that this is almost equal, right, to this average over all the psi's, right? So I'm going to do it in a shortcut like this. And if you think about it, what is this average over all the psi's, right? This is just the unity matrix divided by a Hilbert-Smith dimension. So we have that it is equal to 1 over the Hilbert-Smith dimension trace of A. Okay? And this is... so this is a very special case of the thermal of the Gibbs matrix for beta equal to 0. Okay, so this is a special Gibbs state of infinite temperature. Okay, so what did we learn? What we did learn is that almost any state gives thermal expectation value. So this already helps us or convinces us that we are in the right track, okay? Because we had this problem that our results were dependent or sort of dependent on apparently dependent on the initial conditions, but now we see that actually for almost any state, if you take it on random, the expectation value is thermal. Pretty interesting. Now, another thing that you can do even more than that, which is even more interesting. So let's do it there. So now we're going to take out a piece out of this. So it's a local piece. Well, actually, it doesn't have to be local. But we're going to take a piece out of this Hilbert space, and we're going to call this piece HS, and all the rest. So this is H, yes. This is the entire thing, and the complementary is going to be HB, like it's a bath. Okay, so this is going to be the system and this is the bus. And the entire Hilbert space, right, is just a product of the system and the bus. Okay? And what we are going to do is, okay, let's put this A also inside just for you to understand what's going to happen in the future. So now what we are going to ask, the question is, if I take a random state from the entire Hilbert space, okay, but now I'm not going to, I'm going to constrain it a little bit. I'm going to put it from a shell of, or roughly some energy, okay? Okay, so it is a state which has an expectation E plus minus epsilon, let's say. Okay, so this is the tiny shell of energy, okay? And so I'm going to take random states out of that. So this state is living in the full Hilbert space, okay? And now I'm going to ask, if I'm going to look on the density matrix of the system, so where should I write this? I'm going to look on the density matrix of the system, which is defined. Density matrices are fine, right, Dorit? And so I'm tracing out the bus, okay? And I'm tracing out the bus of some state psi. And let's put here E to remind that it has a certain energy E. Okay, it's not an eigenstate. It's a state which has an expectation value very close to E. Okay, so this is the question. Now I'm going to ask, if I'm going to take this state at random, what is going to be rho s? Okay? And the remarkable result, which you can already guess from here, okay, is that this rho s is going to be exponentially close to exponent minus beta h. So this is another theorem which is called. I'm going to tell you all the references at the end, so don't worry. NEH.
No, HS or...
Here it is HS. Sorry. Canonical typicality. זו שאלת המיליון, כאילו תרגלתי אז... כמה זמן עוד יש לי? ואז... אוקיי, אז לא הגעתי ל-ETH, מצוין. יש לי כבר רבע שעה נגיד? אני לא הסתכלתי על הזמן. בסדר, אני אעשה את זה זריז, אוקיי, אין בעיה. אז לא תראו את התוצאות המעניינות. מה? לא, אני הולך לאט בכוונה, אבל זה לאט מדי, מסתבר. אז, okay, so this is another thing that we can get is the canonical typicality. Okay, so what it means? It means that not only we can get just the infinite temperature, we can also get the finite temperature if we are restricting ourselves to a certain energy. Okay, so we can basically already on a good track, but still. It's using the Levi's lemma. It's basically the Levi's lemma. Okay, just the only thing which is technically harder is that this is done for matrices and this is done for a function. So what you're doing is you're expanding the function in some sort of basis of operators, and then you use the Levy lemma. It's a kind of like a workaround. But I'll give you the reference so you can see. It's not very complicated proof. It uses this. So this is all nice, but this is statements about random states and has nothing to do about thermalization. It just says, okay, what are expectations and doesn't tell us how things evolve with time. And also it does not depend on Hamiltonian, which Yuval was asking, which looks kind of absurd. Okay? So now let's go a little bit further. Still on the rigorous path. I think I do want to say this, but maybe I'll do it faster. So another thing that we can do, which was actually done already in the 20s of the previous century by von Neumann. It was done in German, so no one understood this. But later was translated and done a little bit better. So there is, so I'm going to state it as von Neumann. I'm probably not writing his name correctly. And then it was done, I think, by Tomulka. No, not Tomulka. This one, sorry. This is Peter Ryman. So it's a very. So this is, I think, 2008, and this is 1920 something. I don't remember there, but you'll have the references. So this is about the dynamics. So this is now about the dynamics. And it's also an awkward statement. Also, Yuval is not going to be happy.
I'm happy, you know.
I'm joking around. So now take so imagine take an initial state. It's also a rigorous statement. Yeah? So it is initial state. It can be pure, but it also is generalized to mixed state. And I'm not going to, since I don't have time, I'm not going to specify it precisely. But it is. I can write it, of course, as a superposition of eigenstates of the Hamiltonian. And the requirement is that it contains a lot of those eigenstates. A lot means we are going to be, I'm going to call it just a lot. I'm just going to call it the effective. So this is the number a lot. Okay, the bound is going to depend on this a lot. Just a hint on the physical side of the matter is that every initial state that we can prepare in the lab contains exponentially many in system size. Okay, the only exception is the ground state. Okay, the ground state we can prepare, and it's not going to contain a lot of energy states, maybe very low temperatures, but any finite temperature state is going to contain exponentially many in system size energy states. Okay, we cannot prepare other states in the lab. Okay, so it's okay. It's a physical restriction, but not a mathematical one. And then what? And then there is an assumption on the Hamiltonian on the spectrum. And this is a very mild assumption. It says that the spectrum can be degenerate, but the gaps cannot be. Okay? And I'm going to write it down. Non-degenerate gaps. What it means? It means that if I have E alpha minus E beta, and I know that it is equal to E alpha prime minus E beta prime, then this must say that alpha is equal to alpha prime and beta is equal to beta prime. Cannot be anything else. Okay? In other words, if I calculate all the possible gaps in the system, they never repeat. Okay? So under this very mild condition, okay, which is satisfied, well, it's not satisfied for non-interacting systems. We need to stop.
2 minutes.
Okay, I'll try, do my best. Under these conditions, we have not thermalization, but equilibration. It means that, remember this decay, then this thing happens, okay? So you converge to a plateau, but it doesn't say that this plateau is the thermal plateau. Okay, for this we need ETH. Okay, what is nice and surprising, it does not depend on Hamiltonian. And this was the main criticism for von Neumann. People said to him, no, it's impossible.
Just Riemann Leibniz, isn't
It's not so, no, it's not so.
T large.
Yeah.
If the terms are non-zero.
Yeah, but okay, you're right that it's connected to the phasing, and you need to count the terms and estimate them precisely. So this is already nice. It says that basically, if you have a generic initial state, you are already good. The only things that you need to show, is that this plateau is a thermal plateau.
And that's the.
Yeah, that's the ETH. So I'm going to state this because I see that I'm not going to. Huh?
This you already did?
No, because the plateau is given by the initial conditions.
You told us that they don't matter.
I told you that if I take a random state, they don't matter. Okay, but I didn't tell you. That this this is true for any initial condition. So I'm trying to see in what I can do in 2 minutes. So basically, maybe I'm going to do the simplified ETH very very fast. I'm not going to show energy dependence. So basically, what we can do better to connect it at least to pseudorandomness. So in order to proceed, we need to recall what we had. And we had, I'm reminding you, we had this. Okay? And so what we see from here is that the very important creatures which appear in this unitary evolution are what are called matrix elements, diagonal matrix elements, and off-diagonal. So what I'm going to do is basically assume, okay, so now I'm going to assume something crazy. I'm going to assume that all the eigenstates are random. Okay, so I'm going to assume that basically C alpha, I'm going to state precisely what I'm telling you. So C alpha multiplied by Hilbert space dimension is just normally distributed. Okay, so this is an assumption which is a paraphrase. This is not what was done in the initial work, but this is a paraphrase to what is called as Berry's conjecture. And this already conjecture is not for all systems. It's for only a special class of systems which are called quantum chaotic systems, which applies for quantum chaotic Hamiltonians, okay, in the sense that Shira was telling you. Okay, now I want to show you because it sounds crazy. I want to show you how it looks. Okay, so this is the C alphas so the bottom row what you see is you don't see. So the bottom row is a chaotic model. Okay, so you see it approaches I only run for kind of small system sizes, so it's the blue ones is chaotic, and the red is integrable model, and you see that the distributions are very different. Okay, and now under those assumptions, okay. No, this is a physical model. Okay, we assumed, I made a crazy assumption that you shouldn't believe, that the eigenstates of a physical Hamiltonian, not a random Hamiltonian, there's nothing random in this model. Huh?
For which eigenstate?
I took a high energy states. I thought ground states is special. Okay? So this is a physical model with no randomness. I just compute the eigenstates with diagonalization. I create a histogram. I see a nice Gaussian. Okay? So this crazy assumption appears to work, but it does not work for all states. Okay? So there is here some things that I need to refine, but I'm not going to do this. So this is this assumption how it works. Okay. Now we already restricted to a certain model. Now if we do this, what we can do now easily, we can calculate the. Yeah. Okay. I'm going to state the result. I'm going to state the result, and I'm going to finish. So the matrix elements. You can see, okay, so this is just a sum of normal distributions. So it is a normal distribution. This is also a sum of normal distribution. It is a normal distribution. In order to get it, I just need to calculate the average value and the variance. Okay, I can do this. It's pretty easy to do because it's just average over unitaries. I'm skipping this. And after you do this, you get the average. Okay, plus something which looks like this. When n alpha beta is just n alpha beta is just a normal this number. Okay, n alpha beta. And so this is a simplified ETH. I'm calling it simplified ETH. And using this ETH. What we can do, okay, now you can take this, you can take this assumption, put this inside here in the evolution, okay, and you can show that this value is just the thermal value, okay. This is basically the trick. Now, what I didn't tell you, and those are the details which are, in my view, less important. Is that here the energy does not appear in any place, but in fact, in the not simplified version, the average value depends on the energy, and also Hydra is energy dependent, so it's more intricate than this. But if you want just to understand how the randomness emerges, this is the only thing. The physical part is that this guy is just the thermal value. And the connection to pseudo-randomness is that here I made a crazy assumption on all the states. Okay? In fact, the way it is originally derived, this was the motivation. People thought about it in this way. But at the end, what I need to assume is not this. I can start with this. This is why it's called eigenstate thermalization hypothesis. Okay? And if you look on this square, you can see that this assumption is much weaker. Okay? Because it looks on the expectation values, it just wants the expectation values to be random of a local observable and not the entire thing like I did. Okay, so you see that while I started with a total randomness, what is actually required is pseudo-randomness, and this is the essence of ETH. Okay, so the requirement of the eigenstate thermalization hypothesis is much weaker, and this is the connection to pseudo-randomness. Okay, it was way too fast at the end, but I hope that you got the gist.
I suggest we do. I don't know how to use this. Where is the place? Here. Okay. So we've seen several definitions, and I think, to me, the connections between them are much, much clearer now, but I don't know if it's correct. It's clear in my mind, but I don't know if it's correct. So I think we've seen the definition of randomness by Tzvika. Tzvika, are you here?
Yeah.
Yes, okay. So we've seen the definition of by Tzvika, which is pseudo-randomness, pseudo-random unitaries basically two definitions. One is the T-design, which is information theoretical, and the other is the computational, in which we actually need to distinguish between a polynomial number of samples or of queries, but with polynomial power, assuming some computational assumptions. So that's one approach, cryptographic approach, and Ori's approach was something that seemed. He also used the word pseudorandomness. In my mind, it's more randomness than pseudorandomness, in the sense that basically Ori was describing a way to distribute random unitaries, to sample random unitaries by walking on this expander in the unitary group, and that distribution is basically epsilon close in some sense to har random. So once you sample from it, if I'm not mistaken, and Zvika and Ori, please correct me, if I'm not mistaken, one can show that the output for every, if you fix L, you would get an epsilon net, and that output distribution will be a T design, an approximate T design for any T. Because
okay, so there's a trade-off. You can go from epsilon net to a T design. So the point with T design is that you can make like multiple queries. So you're going to lose like a factor of T when you go from an epsilon net to a T design. So you're going to have like an error of epsilon time. You have a union bound.
But what I'm saying, but just a second, the epsilon net, I think, is not what Ori was constructing. He said it's an epsilon net, but in fact it's stronger than just an epsilon net. It's more uniformly distributed. If I'm not mistaken, all the arguments that you're using and that all these expander on groups arguments, they actually talk about the fact that it's evenly distributed on those epsilon nets. And so it's stronger than just being epsilon nets. It's actually close to har random if you look at the right resolution.
Sure, that's not okay. Sure,
that's not the point.
That's fine. That's fine. But you're still getting a penalty if you go. So what I think what Oli was talking about was like a one query, like sort of a you're counting the distance if you have one query. And indeed, when you use Solovay-Kitaev, for example, right? You approximate each gate within epsilon, but actually you need to take epsilon to be sufficiently small so that you can take a union bound over all gates in your circuit, and together everything is actually going to be close to the unitary. So you're actually going to get a penalty of if you think about it as a T design or as something that needs to work if you do multiple queries, then you get your epsilon gets multiplied by the number of queries. So I don't know if it's a subtlety or not, but so if you're trying to go from an epsilon net to a design, then you're like the trivial way to do it is to get a penalty of the T. Is it not clear? I thought I was saying something that's fairly.
Well, I thought that once you get an epsilon net, then no matter how many samples you take from it, you will not be able. You will be able to distinguish. Okay, you want to actually. I see. So you can't stick the epsilon into the approximate T design. You actually inherit the epsilon into the T. Okay, so you're saying
you're going to have the approximation is going to be epsilon times T. You're going to be epsilon times T close to a T design.
I see. Okay, so these notions are tightly related, and then there was a notion of pseudorandomness, which you showed is somewhat connected, but it's not the same, the computational one. And then there is this notion that Yevgeny and Shira were talking about, which is sort of if you have a small window, a local window, and then things look random even though the state are in fact deterministic. So I don't know, if did you have thoughts of how we actually take the pseudorandom or random matrices or states and connect them with what? So is the notion that Shira and Yevgeny was talking about, is this somehow related to pseudorandomness? This is basically the question. I don't know if anybody has thoughts about this.
You also refer to this idea that we were discussing maybe.
Right, maybe you want to explain it. I kind of lost my the point here. Can you explain this?
No, I think maybe only. So, speaker, maybe I'll tell you something and then you will continue. So, you read in your talk, do you hear it?
I'm struggling. So like,
Here, this is why.
if you can improve things, it'll help.
אוקיי, טוב. אתה שומע אותי עכשיו?
Yeah, now it's good.
Okay, אז אני שואלת, okay, so I'm asking you, so there was this, you were talking about the synthesis problem, which you kind of, in the end, somehow show indicating for it maybe not to exist by other people. And then you were saying something which I don't remember what was the name, about some kind of a problem which is talking about states, and that problem is holds. And after Ori's talk, there was some discussion which Dorit will follow up. I'm not sure how to say it, but somehow that states are kind of related to continuous functions, while in the synthesis problem there is no continuity, and maybe this issue is what is going to distinguish between them. So now maybe, I don't know, Ori or Alon could follow up on this, or Alon maybe. I don't know.
אתה שומע אותי, צביקה?
Not great. The turning on the microphone doesn't work anymore?
For some reason, no.
You're trying and it doesn't work. Okay.
Just speak up.
עכשיו אתה שומע אותי?
I'll try. Yeah, it's okay. Now you're not saying anything, right?
Not yet.
Right.
Yeah.
Okay, so
Okay.
I'm not sure if this is what Tadi was referring to, but at the end of the day, being a T design, is it saying something about approximating moments of the Howe unitary up to T, or like equivalently, approximating how a random Howe unitary behaves under an irreducible representation of the unitary group up to some T dimension T?
Short answer is yes, and yes. So if you actually have like a perfect T design, then it means that the T up to moment T of your unit of your distribution are identical to those of the of a Howe random unitary. And the approximate, now you're asking how do I approximate it? So some notions of approximation are directly talking about moments, about that the moments need to be close under some metric. And others talk about like other ways to distinguish like these channels, the channels that are basically sort of like you get by like sort of twirling some input with this distribution of like T copies of this of your unitary. So I hope this answers your question.
Yeah.
So yes, a T design like a non-approximate, a perfect T design is exactly saying that you have a distribution whose T moments are exactly identical to those of Howe.
So my question about the connection between the physics part and the various mathematical parts are, so you were talking about chaotic systems and about autok and about signatures of chaos, and also Yevgeny was talking in some sense about similar things. And the question is, I didn't understand do we know that for random matrices, for pseudo-random matrices, all these signatures appear? All these signatures behave as they behave in chaotic systems?
Well, I'm not sure, but it sounds like a little bit from what you guys are saying that maybe certain signatures that build upon, I don't know, two-point functions, saturating or expectation, while unsaturating would care about certain moments of the.
So you're saying autok could be a 4-moment function, and therefore that would follow from a 4 design.
Yeah, I'm not sure if that's correct, but it sounds like it depends I guess what you compute, they are all random-like in the sense of mimicking certain behaviors of random. So they look random if you compute that thing or that other things. And I guess this connection at the level of the different moments must have some relation because, but I'm not sure what's the exact thing. I mean, I wouldn't think of like an entanglement entity as being a specific moment. So I'm not sure.
Or do you have thoughts about this?
No, I'm still thinking about what I answered. Trying to understand it.
Somehow my feeling was that Ori's notion is stronger than Zvika's notion, but the big difference is that Ori is working in SU2, and he's understanding very well how to sample from 2x2 unitaries. And my guess is that if you can sample well in Ori's sense, you probably can sample well in Zvika's sense, but for 2x2 unitaries. And Zvika's sense is like, I think makes, is it correct, Zvika, to say that your pseudo-random unitaries have more meaning when the dimension is very large?
I'm not sure. Let's sort of define what we mean by Ori's sense, because there was a graph and there was like a lot, like a combinatorial object. So, but I want to talk about like a distribution of unitaries. So we're talking about like taking this subset of gates and just doing like a random walk on them. This is like the
So Ori's random unitary is you fix some your key length is the length of your random walk, and you walk k steps and you get a unitary.
So I think this is the connection between an epsilon net and a design. So in the sense that you're going to get, you're actually, that you're actually getting close to an actual, like to all the unitaries. You're actually going to be close to them, but this doesn't mean that you're going to be indistinguishable when you make multiple queries. And definitely, we're talking about T designs here. Like the computational notion is this is something different altogether. But I think that this is like maybe like a way to get that you can get, like, for example, a design from like this, from an epsilon net. So but I thought you said something, so maybe what you were saying is more than this. So
I'm not sure.
You're saying, so which notion is implying now I think now like we sort of said what always the notion is. What is my notion that you're talking about?
That always notion would give a good T design, I guess, for 2x2
T design.
unitaries.
Okay, yeah. So good. So
or that's what David said, actually.
Yeah. So that there is a connection between like an epsilon net and a T design. And but you're getting this penalty of like the union bound. You're getting a factor of T. So when T is very big, like when you're going to need to sort of basically like sort of tune your epsilon so that you're going to have like a sufficient like your epsilon is going to be sufficiently small so that you can support this.
So maybe I think we are connecting. We have connected something like we haven't yet connected the fourth talk, and the first three talks seem to be connected to some extent, and lots of questions arose whether everything that we said is true, or at least one.
There's also the connection to the pseudo-randomness in the same sense of Zvika with these words of Vazir.
Right. Wait. This is too complicated for our for this discussion. But just to ask about what Yevgeny was talking about. This is not about random unitaries, but basically, if I understand correctly, the conjecture is, or one could state a conjecture, that the eigenstate thermalization hypothesis would work for chaotic Hamiltonians. Yeah. Is this really, and so one would somehow guess that basically chaotic Hamiltonians, even though they're deterministic, would behave like random matrices.
Correct.
Right? So, okay. Maybe this is a...
All you were suggesting something that your definition implies something about continuous function, or something about nice function, smooth function. Can you just repeat it?
Yeah, Zvika, maybe you can make a sense out of it. I don't know how to state it exactly, but what we do, we generate a net or a random scheme, and I think that the spectral analysis, what it tells us is that somehow for an oracle who can only access our function by choosing a test function, a continuous or smooth test function, and integrate it against our net, our net is indistinguishable from Haar uniform. But if he can take any function, then he can distinguish. That's my intuition.
Right. So one way to define like approximate designs is to say that you're looking at a class of So I was talking about class of distinguishers that just take an algorithm and do some number of queries. But you can also think about taking like degree T polynomials. So you're saying that I'm going to take a degree T polynomial in my unitary, and the expectation for any degree T should be closed. And this is actually called, so I thought it was actually related to what you're saying, because this notion is called tensor product expander. So I thought that this was going to be like this notion that maybe you're talking about, but I guess that's not exactly it. Yeah, so it's sort of like, yeah, you need to choose like you can think about each one of these like approximation notions as choosing a class of distinguishers. So one class that people choose is really like taking polynomials of a bounded degree. So you're talking about general smooth functions. I don't know. Like I'm not familiar with like this this notion. I mean, maybe it'd be interesting to see what it means. But this is what I know.
So I think is this not working?
It's okay, Dorit.
It's not working. Okay, so.
It's fine. I can hear you.
Yeah, no, it's not. So, in the interest of time, I think we will roll again. But I just wanted to say, are people over the Zoom other than Zvika, for example, Moshe? I thought that you would have some comment. So if Moshe or anybody else wants to say something from the Zoom, it would be great. I don't know if Moshe is still there. No? Yes? No. Okay, so let's thank all the speakers of the day. And for those who are staying for the students' meeting, there is fruit outside, and we will have, I don't know.
Dorit?
Yeah.
Sorry, if I may, just also I wanted to. Sorry for being remote. I also wanted to thank the people at Weizmann who were like sort of organizing all of this this event. Mostly to Karina, our department admin, for taking care of everything. To the people from our department, also of course to the people of Lupati who were actually sort of making this venue available. So really, thank you all very much. And obviously, Dorit, please mention the Talia and you and Talia, of course, for organizing. So really, thanks a lot to everybody who helped make this thing happen.